Welcome back to another Explainer. Today we're exploring something so incredibly fundamental, so omnipresent, that you are literally experiencing it right this very second. We are talking about gravitation. It is the invisible tether that dictates everything in our universe, from the simple, grounded act of an apple falling from a tree in your backyard, all the way to the majestic, swirling formation of distant galaxies.
Okay, let's dive into this. On the agenda today, we've got the universal invisible tether, the math behind the pole, planetary orbits and satellites, escaping gravity's grip, gravity in our daily lives, and finally, Einstein and the cosmic order. Let's get right to it.
Kicking things off with Section 1, the universal invisible tether.
Before we get into the heavy math, let's just ground ourselves, pun totally intended, in what this force actually is. At its core, gravitation is the universal, fundamental force of attraction between any two masses. If a thing has mass, well, it pulls. It's kind of wild to think it really is that simple, yet incredibly profound. It acts as a central, conservative force, which basically just means it always pulls directly along the invisible line joining the centers of two objects, creating an inward-directed field. It is the ultimate cosmic glue, holding the whole shebang together.
Now, humanity has been trying to wrap our heads around this for a really long time. Way back in 350 BC, Aristotle thought objects just fell because, it was their natural motion. Fast forward a bit to 628 AD, and Brahmagupta correctly proposed that Earth specifically attracts objects toward its center. Then in 1609, Kepler gave us the laws of planetary motion, but it wasn't until 1687 that Isaac Newton did something truly revolutionary. He brilliantly unified Earth physics, like that famous falling apple, with space physics, proving that it's all literally the exact same force.
Moving right along to Section 2, the math behind the pole. So we know this invisible tether exists everywhere, but how do we actually calculate its strength? Well, this was Newton's massive breakthrough, the universal law of gravitation. It says that every single particle in the universe attracts every other particle. The strength of that attraction is directly proportional to how massive the objects are. But, and this is an absolutely crucial but, it is inversely proportional to the square of their distance. Because it's an inverse square law, that means the pulling force weakens significantly and super rapidly the further apart those objects get.
Now, what's really interesting about this equation is how elegantly simple it is when you break it down. Force equals big G multiplied by the mass of the first object times the mass of the second object, all divided by the distance between their centers squared. You don't need to be a theoretical physicist to appreciate this. It just means bigger masses equal a bigger pull, and greater distance equals a dramatically smaller pull.
Okay, this next part is a classic point of confusion, but it is so cool when it clicks. It's the difference between big G and little g. Big G is the universal gravitational constant. Its value was famously verified by the Cavendish experiment, and it is the exact same everywhere in the entire universe. Little g, on the other hand, is the specific acceleration due to gravity on a specific planet, like, say, right here on Earth.
Think about this exact number for a second. 9.8 meters per second squared. That is the specific acceleration keeping you securely in your chair right this very moment. But because of that inverse square law we were just talking about, this number actually changes. If you hike up Mount Everest or if you dig way down deep into a mine, you are changing your distance from the Earth's center. And because of that, little g actually weakens. Crazy, right? All right, zooming out a bit for Section 3, planetary orbits and satellites. Leaving the surface of the Earth behind for a minute, remember Johannes Kepler from our timeline earlier? Well, he gave us three incredibly elegant laws that govern the precise timing and movement of our solar system. First up, planets don't actually move in perfect circles. They move in elliptical orbits with the sun acting as one focus. Second, as a planet gets closer to the sun in that ellipse, it actually speeds up, sweeping equal areas in equal time. And third, the time it takes to complete an orbit squared is proportional to its distance from the sun cubed. It is just absolute mathematical clockwork. But hey, this isn't just abstract space math. This orbital mechanics is the exact reason why the moon, our natural satellite, stays up there in the sky. And it's the exact same physics we use to keep human-made artificial satellites up there too. If we didn't have orbital velocity perfectly balancing Earth's gravitational pull, those satellites would just crash straight down. And that means no GPS navigation on your phone, no modern weather forecasting, and absolutely no global space communications.
Which brings us to Section 4, escaping gravity's grip.
So,
If gravity is constantly pulling everything inward, what does it actually take to completely break free? Well, it requires something called escape velocity. This is the absolute minimum speed an object has to reach to blast away from a planet's gravitational pull and never get pulled back. In physics, the gravitational potential energy in a bound system, picture a rocket just sitting there on a launch pad, is inherently negative. To overcome that negative energy and hit zero, you have to do massive amounts of physical work.
And for Earth, that work translates to a speed of 11.2 kilometers per second. Let's just pause and think about that for a second. Kilometers per second. That is roughly 25,000 miles per hour. There is literally no way around it. That is just how incredibly fast humanity has to travel to escape Earth's gravity for our space exploration missions. It is a staggering testament to the sheer strength of Earth's hold on us.
Next up, Section 5, Gravity in Our Daily Lives.
Now you might be wondering, why does all this cosmic math matter to you and me on a random Tuesday morning? Well, because gravity dictates your everyday reality. It's the reason objects fall when you drop them. It directly determines your physical weight on a bathroom scale, for better or worse. It's absolutely critical for engineers who have to factor it in when building bridges and skyscrapers so they don't, collapse. And perhaps most beautifully, the high and low ocean tides you see at the beach, those are actually a massive daily visual reminder of the moon and sun's gravitational pull interacting with Earth's oceans.
And this brilliantly illustrates one of the greatest paradoxes in physics, especially when we compare gravitation to the electromagnetic force. See, gravity is always attractive, whereas electromagnetism can attract or repel. But look at the strength here. Gravity is by far the weakest of the fundamental forces. I mean, you overcome Earth's gravity every single time you pick up your smartphone off the table. Yet, because its range is infinite, this incredibly weak force is what structurally organizes the entire universe.
Finally, we reach Section 6, Einstein and the Cosmic Order.
Let's zoom all the way out to the farthest reaches of the cosmos, and really the limits of human understanding. For over 200 years, Newton's laws were treated as absolute gospel, and they are undeniably brilliant. But eventually, astronomers realized they kind of hit a wall. Newton's math couldn't precisely explain the slight wobble in Mercury's orbit around the sun. And when dealing with massive cosmic anomalies with impossibly high gravity, like the formation of black holes, Newton's equations just fail completely.
Enter Albert Einstein. He provided a mind-bending solution with his general theory of relativity. Einstein proposed that gravity actually isn't a pulling force acting across a distance at all. Instead, mass literally bends the very fabric of the universe. Gravity is the curvature of space-time. Think of a heavy bowling ball sitting on a trampoline, making a dip that smaller marbles naturally roll into. Our invisible tether is literally the bending of the cosmic fabric itself.
Which leaves us with this final, thrilling thought. Gravitation truly is the foundation of cosmic order. It connects everything, from falling apples to orbiting galaxies. But if what we thought was invisible pulling force turned out to be the literal warping of space-time, what else is the universe hiding in plain sight? I really hope this explainer sparked your curiosity to look up at the stars tonight and just wonder. Thanks so much for exploring this with me, and I'll catch you in the next one.